Okay, so maybe there is part of the answer to this question in this presentation. I will not say more. This presentation is called a Prospective on PAHs. I'm going to talk about the context very briefly and then try and give you what looks like a prospective. I want to start with a disclaimer. The first thing is I need to say once in this presentation that PAHs or PAHs mean polycyclic aromatic hydrocarbons. So this way I've said it. And this presentation is non-exhaustive. It's a relatively personal view on PAH studies. So we can call that a confused bias. So it's a heavily biased presentation. I think it's often the case, but it's good to say it. So it presents an approach which has been active for about 15 years in Toulouse, which is also active in other places. There are contributions in France and elsewhere, of course, on this topic in many different institutes in the world. And the approach that we developed in Toulouse is the following. It combines several expertise in observations, of course, in signal processing, quantum chemistry calculations, and also experimental lab work, which is a very important part. So I want to talk about the context because this is useful to understand what comes next. And let me start with very general context. This is the a view of our galaxy, the Milky Way, from inside. As Doug said, it's difficult to see from outside. And this is in the infrared. This is imaging in the infrared. But if you take a spectrum of this galaxy, of our galaxy, and also many other galaxies, this is what you will obtain. The mid-infrared spectrum of galaxies is dominated by a set of bands, which were called the aromatic infrared bands. And the attribution of these infrared bands, which are ubiquitous, was provided already now over 35 years ago. And it's called the PAH model. And the idea, which was proposed by French and American teams simultaneously, almost simultaneously, is the following: is that you have these large aromatic molecules which are pumped through the absorption of UV photons of stars through their electronic absorptions. So perhaps this is connected to the diffuse interstellar bands. They are pumped this way, and then they cool down through vibrational emission in the mid-infrared, and each of these bands that you see here is connected to specific vibrations of the molecules due to bonds, either the carbon-carbon bonds or the carbon-hydrogen bonds. PAHs play a very important role in the interstellar medium and in galaxies. So I showed to you that they are UV pumped, so it means they absorb the UV radiation from stars, but this radiation can also ionize the pH. And this way you will eject an electron, and this electron will collide with the gas. And so this means that you heat the gas with the interaction of UV photons of stars with PAHs. This is very important because this determines how well the radiation from stars is coupled to the gas, how efficiently you can heat the gas with the radiations of stars. And so it's also connected to the star formation efficiency of galaxies. Since stars only form in cold gas, the star formation rate of galaxies depend on this photoelectric heating process. PAHs also provide a surface for the formation of H2. This is something that has been the topic of many studies. Here I provide some references. It's also not exhaustive. We could write several reviews on all these aspects. There are many different contributions. But so they play a role in the formation of H2. It's very likely, although it's not fully understood yet how this actually works. But it's clearly a fundamental process, again, because stars form in molecular clouds. So you need to form H2 to form stars. So again, you see here that this has profound impacts. PAHs participate in the organic chemistry. From about 5 to 10% of the cosmic carbon is in these molecules. So of course they play a role in chemistry, and there are several ways that they connect to the rest of the universe in terms of chemical links. One of them is the top-down chemistry that is illustrated in the left, for instance, for the formation of fuel rings. But there are other pathways of destruction of large carbonaceous systems, which can lead to smaller hydrocarbons, for instance, as was proposed by Jerome and following papers. And also something that is quite important, and that's a recent result, is the detection of PAHs in cold molecular clouds through radio astronomy. And so there are detection of cyanonaphthalene and endene, which are aromatic hydrocarbons, polyaromatic hydrocarbons. So, you know, for a very long time, people have said, well, you know, your pH model, it works, but until we don't have a specific detection, we're not going to believe you. Now, thanks to radio astronomers, people start to believe infrared astronomers like me. So thank you very much for those in the room. But it's something that is interesting also because it shows that these gas phase molecules also exist in very cold environments. And this links to the chemistry also. How does these small aromatic hydrocarbons relate to the larger ones that we see in emission? So the way we've been analyzing infrared observation is the following. This is a Spitzer image of a reflection nebula in GC 7023. And you have a star that is at the bottom here. It's a B star that's illuminating a molecular cloud. It's the dark region in the upper right part of the image. But so there is this transition region for the molecular cloud to the regions where it's highly irradiated by the B star. And this is spectral mapping of this region in the mid-infrared. And on each pixels here, you have an infrared spectrum like this in the case of Spitzer. And what's interesting is that you see variation of these mid-infrared bands as you go from the molecular cloud to the star. And what we and many people have been doing in the past 10 or 15 years, thanks to this hyperspectral data, is to analyze these variations, to try and understand the evolution of these aromatic infrared bands and how they relate to the photochemical evolution, for instance, of the species. So as I said, one of the approach that we pushed was to use signal processing techniques, and one that we've been using for a relatively long time is called blind signal separation, which allows to decompose these observations, these hyperspectral cubes, into a set of components, spectral components. And here on the left, you see 3 spectral components that were extracted from the data. And on the right, you see their respective spatial distribution. And from that, you can build some interpretations. And for instance, you can have this chemical evolution from, let's say, pH clusters to free-flying pHs when you go here to this, the surface of the molecular clouds, to here in regions closer to the star, to the ionized species. If you go really to the inner parts, you can move to a more harsh chemistry where you dehydrogenate the molecules, and they can form, for instance, the fullerene molecules. So this is the kind of scenario that you can create, but this, of course, relies on a large number of theoretical and experimental studies. So the experimental studies here are in red and the theoretical ones are in blue. This is, again, non-exhaustive. It's just to illustrate the fact that to build this interpretation, and of course, we also have models behind to do the things in a more quantitative way, you need really the support from experimental and theoretical work. Okay, so I'm now going to turn to the prospective. Again, it's very biased, but clearly in the field right now, as was shown by Pierre-Olivier, one of the main changes is the launch of the JWST this December. You know, with this mission, we will see these aromatic infrared bands, these PAHs, pretty much everywhere in the galaxy and in other galaxies. So we will have these signatures, and we will need to understand what is behind this emission mechanism and what is the chemical evolution of the carriers to also provide the tools for astronomers to interpret the observations. There are many several observational programs which focus on this, on the study of these infrared bands, including in the GTO. But of course, we are very interested in this program, which is an early release science program, which was mentioned by Pierre-Olivier this morning, which is now called PDRs for All, and is focusing on the Orion Bar region. This is a project which is for which the PI team is composed of Els Peters, Emily, and myself. And the core team has 20 scientists, and 3 of them are from the PCMI community. And amongst the science collaborators, there's 130 scientists. And I think it depends how you count, but 10 to 20 of them are also members of PCMI. So clearly, a large fraction of the PCMI community is involved in this project. So it's 35 hours of observations, and currently, and it's unlikely that it will change now, the observations are planned for September 2022, which is the start of the visibility window for Orion. And as it was said by Pierre-Olivier, for these programs, all data will be made public immediately, although we will provide enhanced data products that will be better than what the pipeline provides in principle. Very briefly about this project, this is the Orion Bar region. This is what we will obtain in terms of field of view for the imaging in the near infrared and the visible, so large field of view. In imaging, so this is just some simulations that were done in Toulouse of the observations with the instrument simulators. With MIRI, we will obtain a much smaller field of view of the Orion Bar. This is because we need to use short integration, so we cannot use the full field of view to avoid saturation. So we can zoom into the Orion Bar. These are the protoplanetary disks that Emily has mentioned. So we will also observe these protoplanetary disks. And if you switch to a more, let's say, physical view of the region, this is what it looks like. Here you have a multicolor image where the blue part is H-alpha emission observed with the Hubble Space Telescope. So this is a region where the gas is fully ionized and it's hot, it's 10 to the 4 K. Then you have the ionization front, which is where electrons and ions recombine, and the temperature cools down to around 1000 K. And you enter the green zone, which is the neutral atomic gas. And then if you go deeper into the cloud, you have the HH2 dissociation front. That's where the gas becomes molecular, and it cools down there to temperatures below 100 Kelvin. So you see there is a very strong temperature and also density, in fact, gradient inside this region. So we will obtain, and that's perhaps the most interesting part for us today, and that's what concerns also these aromatic infrared bands and PAHs. We will obtain spectroscopic observations in all these regions. So if you look at this this mosaic, this rectangle shaped, this is the region where we will obtain the spectroscopic mosaic. And basically, I don't know if you see the pixels here in this image, but you have to imagine that for each one of these pixels, we will have a full mid-infrared spectrum, like the ones that are shown here. These are simulations that combine a number of hypotheses, but they give an idea, these simulations give an idea of the spectral richness of this data, which will be gigantic. And of course, this will be, from September 22 and ongoing, this will really be our database to assess the physics of photodissociation regions, but also to work on the pH emission. Okay, one thing we want to do, and that's going back to the signal processing methods that we will use for the analysis of this data, is we will have very rich data, but we want to do even better, and we want to recover data with the highest angular resolution of the JWST imagers combined to the spectral resolution of the spectrographs. So the methods we developed to do that is to use what we call fusion methods, which basically are based on a description of the models of the instruments. So we have a direct model of the instruments, and we formulate the fusion problem as an inverse problem. We use that to create synthetic scenes from the spectra that were shown in the previous slide. And so you see here, this is the synthetic scene of the Orion bar. And we have here in this orange region, the hyperspectral cube, which is simulated. And if you take a point in this spectral cube, this is what you obtain in the simulation. And then we cast this synthetic scene through the instrument, the direct models, and we get a simulated multispectral data set. Okay, so you have these images, and you have these, the spectroscopic information here is of course lost because you go through the imager. And we have a simulated hyperspectral image where you have still some spectral richness here, but you have the noise that is added. And if you look spatially, because we don't really see here in the large images, what you see here is that for the synthetic scene, you have the full texture in terms of spatial details, which you keep in the multispectral image, but you lose the spectral information as illustrated by the contrast lost here in the color image. And in the simulated hyperspectral image, of course, you see that you lose quality in terms of spatial details. And what you want to do is to recover this. So this is work that was done by Claire Guillotot during her PhD thesis. She just defended last week, and there are 2 papers presenting these methods. I will not go through the details, but basically she developed a very smart and fast method, because you have to realize that these data sets are very large, several gigabytes of data for just one scene. So if you want to do this, use these algorithms, you better have something that is smart and fast. And this compares the reference synthetic scene to the resulting fusion method. And you see that in this 3-color image, you recover the data quite well. And if you take a spectrum here at the ionization front, you see that if you compare the reference and the fused data, you get something that is extremely similar. And we also tested these methods on Hubble and Muse to test that on real data, and we have very successful results, very encouraging results. And of course, we will do this on the real data, hopefully next year. Okay, we also still in the signal processing range, needed to develop specific blind signal separation analysis tools. Again, because the size of the data is very large, it's much larger than Spitzer in terms of number of points. And so the initialization methods that we used before were inappropriate, because it required to do some Monte Carlo analysis a posteriori, which was extremely time consuming. So Axel Boulet developed a method of initialization of this blind signal separation algorithm, which is based on finding the vertices of the simplicial cone engendered by the data. And if you initialize blind signal separation like this, you gain a lot of time and you find the right solution, as he has shown. And Sasha Foskino used these methods to test that on archival ISO data, which have a spectral resolution which is closer to that of JWST. And we could obtain a new spectral decomposition of the aromatic infrared bands in 2 different populations. So we find again our pH clusters, the neutral pH spectrum, the cations, and this one, large ionized PAHs, which had been also identified, before, but we were unable to extract it really from the observations. So this was the first time we were able to do this. And also we have this part of the spectrum at 3 micron, which we did not have before. So that's an improvement. And these spectra were also used in the simulated spectra that I have shown earlier. Okay. Also, an important aspect concerns, as I mentioned, the heating of the gas by PAHs. This is something that probably needs to be reinvestigated. The current status is that classical models of dust heating, so by Drain and Weingartner, or by Tillens and Bakes, for instance, include these PAHs, but however, they do not include the detailed molecular physics relevant for PAHs. These papers are at least 20 years old. So, at that time, there were not a lot of knowledge on the molecular parameters for these pH molecules. So what we did recently is to propose a PAH model for the heating of the gas, which is inspired by the model of Laurent Verstraete from the 90s, but using all the latest molecular parameters and to try and compare that to observations. So here are, for instance, the molecular parameters you need for these models. That's where the people doing lab and theoretical work come into play, and this is fundamental. You need, for instance, the photoabsorption and the photoionization cross-sections. So here they are calculated for different size of PAHs based on the theoretical database of Giacomo Milas. You need also the ionization yields. So that's the probability with which the absorbed photon will actually lead to ionization. And this comes from the measurements of Gaby Wenzel. And this is what's important here is that we have first ionization potential and second ionization potential. So that this one is for decations. A very important also parameter is what is called the partition coefficient. So this is the ratio between the photon energy and what is actually extracted in terms of kinetic energy of the electron. To compute this partition coefficient, you can use, for instance, these spectral maps of the kinetic energy of photoelectrons measured by Brechignac et al. I think it was done in Soleil. And here they provide this data, which we can convert into this partition coefficient to put in astrophysical models. Okay, then when you do that, you can compare your results to the observations. It's not straightforward. Something that we like to use is what is called photoelectric heating efficiency, which is the ratio between the energy absorbed by dust in general in form of UV photons to the actual kinetic energy of electrons that goes into the gas to heat it. So when you do that, and this was done by Cornelia Pabst as part of her PhD thesis, these are the points that she derived for a number of nebulae in the galaxy. And this is the model of Tillens and Bakes. And you see that there is an important mismatch between observations and the model. That is a dust model. It's not a pH model. So we redid this analysis using the pH model for different spectral types. These are the continuous and dotted dashed lines here. And the points here in color are the different regions. We include galactic regions, but also extragalactic regions and protoplanetary disks. And what you see is that using a pure pH model, we find a better agreement in terms of the photoelectric heating efficiency that we calculate as compared to what you extract from the observations. So the observationally derived points here are obtained from spectroscopy of PAHs with Spitzer, but of course with James Webb we will, and you see here, for instance, these points here are for the NGC 703 nebula. So that's the spatially resolved observations, but you see we only have I think 7 or maybe 8 or 9 points. So we don't have a lot of information. It's very difficult to do this type of measurements on spatially resolved observations. clearly with James Webb, we will obtain a much clearer view of this photoelectric heating efficiency, for instance, in the Orion Nebula. So it's probably important that we revisit heating in PDR models, or the concept of gas heating in galaxies in general around that, including a molecular description, or including the evolution of species, sorry. And this is also following the work of Thibaut Schirmer on the evolution of grains inside PDRs, and then to test these models on the observations with James Webb. So I think we should organize a workshop on this specific topic. And this is something we've been discussing with Emily, with Emric, with many people. Probably something that is important to address, and we have the expertise at the PCMI level in France, which is really, I think, unique in the world. One last thing I want to talk about is something perhaps quite new. We can call that, Giacomo Mulas calls that dark paths. It's the possibility to detect new polycyclic aromatic hydrocarbons with James Webb. So it's important to realize that PAHs are most of the time in their ground vibrational state in the interstellar medium. So it means they are cold, and sometimes once a day they absorb a photon and cool down, and you see them in emission. But in fact, we should be able to see them in absorption. There are no reasons why we should not see them in absorption. And with a resolution of around, let's say, 0.2 centimeter minus 1 in the mid-air with James Webb, or Webb, we could, in principle, detect and resolve their absorption bands. And this is interesting, of course, because when they are cold, you don't have this blend of bands, and you can be much more specific. So we started to perform realistic simulations which require first to have theoretical data, spectroscopic data with a high accuracy. So for that, you need a quantum chemical anharmonic calculation to predict the band position and structure. And so this is what Giacomo Mulas has done. And of course, we need to couple that to an astrospectroscopic model, including the instrumental performances. This is the kind of thing you obtain. This is for Indene, which is the species that was detected by Cernicharo et al. If you get this kind of absorption spectrum for a column density of the order of a few 10 to the 15, this is much more than what the column densities that were observed, for instance, in the TMC1 cloud for this species. However, it's also very possible that you have regions where these molecules are much more abundant, and also you can observe non-polar molecules like naphthalene or anthracene, which do not have a dipole moment, and you cannot detect with radio telescopes. Okay, so this is the pure spectra. Of course, you have to include noise. That's what happens when you include the realistic noise for MIRI. And you see, of course, that you lose the information. And this is what will limit your ability to detect this kind of species. An important aspect is that for these studies, and because there are many species, you need databases where you can put the spectroscopic information. And this is something that has been developed also in Toulouse and Cagliari by Giacomo Christine, for instance, this Cosmic PA portal. Okay, and I think that's all I wanted to say. So this is the end of the presentation, but not completely the end, hopefully.
Thank you, Olivier. I think there's a question by Karim.
Yes, I have a question about the presence of these small pHs in cold ISM. What are the scenarios to explain their presence in the gas phase in such environments?
So there are several, there are theoretical and experimental demonstrations that you can form aromatic species in cold environments. I think it's mainly the work of Ralph Kaiser, where they have shown that you can form, starting, I think, from acetylene, but in cold environments, you can form aromatic species. I don't know the details of how you get over the barriers, but it seems that you can in some specific conditions, including cold ISM.
Jérôme, you have a question as well?
Yes, it's about your decomposition, your separation algorithms to separate the pH forms. Did I understand correctly that you're using only the data to make the decomposition, or do you use insight from the laboratory to get spectral signatures?
No, for the decomposition itself, we use only the data. And then the interpretation of the decomposition is supported by theoretical and experimental data.
There's a question by Vianney.
Yeah, I was interested by the data fusion technique. And so I was wondering whether you applied it to existing observations. You mentioned news. I was more thinking of things more related to pHs, like speed zero, for instance, speed zero cubes. And so I was wondering whether you did that. And also one difficulty we had with speed zero data was the lack of knowledge of some instrumental parameters like the intrapixel response function, the exact PSF shape. And so I was wondering whether that was a limitation in the data fusion technique, or whether you can actually infer some of the instrumental parameters using the data you have in hand.
So for the first part, for Spitzer, the limitation is that the overlap between, spectroscopically speaking, between the imager and the spectroscopy is not very large. You only have, I think, 3 of the 4 filters which overlap. And 3 filters is not a lot. For instance, in the NIRCam versus NIRSPEC observations with James Webb, you have, I don't know, maybe 16 filters which overlap, something very important. So it's of course much easier when you have more information. And regarding the second aspect, yes, it's very important to have a very precise knowledge of the instrument details, because in the direct model that we use also to solve the inverse problem, knowing that is extremely helpful. So you can always add some, unknowns to the problem, but it will increase your computational time, and it will increase, of course, the uncertainty of your results. But I think in principle, it's relatively easy to implement. It's just that it will degrade the results probably.
Thank you very much. Are there other questions?
So Olivier, concerning the top-down scenario where you go from the pHs to the coronin, what are the most probable processes that could be at play, that are competing?
So at least in the models, what we find is that so it's really the photochemistry. So it's the absorption of UV photons which allows to jump the energy barriers which take you from a flat molecule to a fullerene. And the competition between this isomerization in a way and dissociation and other processes is the relaxation channels. And in particular, we found that the Poincaré fluorescence, so the emission through you have a very hot molecule, vibrationally very hot. And so you have a probability which becomes important that the fluorescence occurs not through the vibrational bands, but you have energy going back to lower electronic states. And then it cascades down through these electronic states, the ground electronic state. And this is at high temperatures, it's a very efficient channel to cool down the molecules. And so you have a strong competition between this process and this isomerization process.
And could you also have some knockout mechanism where some energetic ion is really removing one carbon atom from the skeleton?
Yes, this is a possibility, and I know there were studies conducted on the theoretical and also in the laboratory with on collisions with, I think, electrons, and you see that you can create defects in these structures. I think in regions like the one we studied, NGC 7023, the abundance of UV photons is much larger than high energy particles. So the dominating processes will clearly be those related to UV photons. However, if you're located in cold environments with not a lot of UV, the processes that you mentioned can become dominant. And it's true also for the gas heating. The gas heating by the photoelectric effect works in UV-dominated regions. If you go to cold molecular clouds, cosmic rays become the dominant source.
Thanks, Olivier. And if there are no more questions, then let's thank the speakers of the morning. And we'll reconvene at 10 minutes before 2 in this room and in this Zoom room.